Hi everyone, my name is Julia and I'm on the communications team here at GLE. Today we'll be working through Module 11.2 Lunar Exploration together. So let's get into it. In this module, we'll discuss the features of the lunar surface, its surrounding environment, and how rapidly the lunar environment changes. We'll explore the dynamic environment that affects the lunar missions and science, such as the interaction between the lunar equipment and the regolith, thermal modeling of the lunar surface, the lunar day compared to the lunar night, lunar gravity, and more. So just a quick note before we begin. Although we are working very hard to find a lander, GLE does still not have a secured ride to take the Lunasats to the moon. The final flight code structure for teams to program the lunar version of the Lunasats is still in development. And lastly, this module is just a first glimpse to get you thinking of what your next steps could be after this online workshop. So let's talk about your mission to the moon. And now let's ask some questions about the moon. So what is the composition of the lunar regolith? What is its density? The moon's albedo? The incident angle of the light where a spot is receiving it from the sun? The location of the moon that we're looking at? And its heat capacity? And most importantly, we'll ask, why is this important? The lunar surface is a harsh environment with variability in temperature, radiation exposure, and much more. If we made the wrong assumptions about where our equipment and where our science will take place, it could affect the performance and yield of our data. For example, if we're assuming a fixed lunar surface temperature, where we assume there are very little differences, it can cause harm to our science. This assumption may also be necessary in other cases, though, and we will discover the consequences of both of these choices in this module. So I'm now going to hand this off to my friend Ben to talk about the lunar surface.
Hi everyone, my name is Ben and I am on the communications team here at GLE, and we'll now go over the lunar surface. So where are we? Where we are on the moon is always a very important question to consider. This determines how much light exposure we are going to get, the thermal radiation levels, and positional logistics such as altitude and gravitational strength variances. And so it's important to understand the different types of lunar surface features. We have the highlands, the maria, the craters, the valleys, the mountains, and also potential landing sites, as we will discover further on in this module. So in regards to the highlands are typically characterized as the light areas on the moon. They tend to be heavily cratered and mountainous. They are also older formations on the moon's surface, typically about 3.8 to 4.3 billion years old. Their albedo, or reflectivity of light, tends to range from 12% to 18%. And just that way you guys are aware, albedo ranges for fresh asphalt is about 4% reflectivity, whereas the albedo for fresh snow is about 80%. And the regolith in the highlands tends to be about 10 meters thick. For the maria, they tend to be characterized as the darker regions of the moon. They're not as heavily cratered and tend to be relatively flat, and they also are newer formations along the moon, so typically about 3.3 to 3.8 billion years old. Their albedo ranges from 5% to 10%. And the regolith in this area tends to only be about 1 to 2 meters thick. For our craters, they tend to be found mostly in the highlands and most abundantly on the far side of the moon. Craters on the moon tend to be a result from impacts, not volcanic activity, which most of the craters on the Earth tend to be volcanic. The crater floors tend to be lower than the surrounding plains, and they tend to be circular in shape compared to being elliptical because of the lunar escape velocity. The mountains along the moon are some of the highest that we have here in the solar system. The largest mountains rival those here on Earth. For example, Zimon Mons tends to be about 7,570 meters when measured from the base of the crater. And these are formed from impacts. Now for the dangers of the moon. So temperature variances along the moon are extreme. The surface temperature ranges from 120 degrees Celsius to negative 130 degrees Celsius. And local temperatures can change drastically as well. The temperatures at the lunar North Pole tend to average around negative 247, and the temperatures around the lunar South Pole tend to range around negative 238 degrees Celsius. The lunar day and nights affect temperature as well. The lack of a large atmosphere contributes to the large fluctuation of the temperatures. Now for some orbital details about the moon. The day and night cycle on the moon lasts for 2 weeks, so this means that there's 2 weeks of daytime and then 2 weeks of nighttime, which tends to equal about 27.3 Earth days to make one lunar day. The axis of the moon is perpendicular to the light from the sun, so there are some permanently shadowed regions along the lunar surface. And the moon is also subjected to tidal forces from both the sun and the earth. And this often results in some moonquakes. The moon is geologically active and experiences these moonquakes. So there are several types. There's the deep moonquakes, which are caused by these tidal forces, thermal quakes, which these are caused from the crust of the moon expanding with the temperature and also the tides. Shallow moonquakes, these tend to be the most dangerous and last a long time along the lunar surface, along with vibrations that can be caused from meteor impacts along the moon. Gravity on the moon is much less than here on the Earth. It's only about 1/6 of the Earth's total gravity. The surface gravity tends to average about 1.62 meters per second squared, and this fluctuates across the entire moon. Here we have a little map of lunar gravity taken by the GRILL mission. Now for radiation along the lunar surface. The approximate annual maximum radiation exposure due to cosmic rays is about 380 millisieverts. The lowest tends to be about 110 millisieverts. Hence, radiation exposure over 14 days will average about 4.2 to 14.6 millisieverts. The absence of a magnetic field and an atmosphere shielding the moon allows for cosmic rays of all energies to impinge on the lunar surface. Now time for lunar dust. So a direct quote from one of our sources: the lunar surface is covered by a layer of unconsolidated debris called the lunar regolith. And due to the charged radiation bombarding the moon, the lunar dust is statically charged and clings to objects. And so this means that it's going to get transported via contact with any scientific instruments that we send to the moon, along with any astronaut's boots. And this can reduce visibility and the performance of equipment, such as our solar panels. And so some scientific studies will refer to the very top layer of the lunar regolith, or dust, as a regolith fluff. The bulk of the regolith is a fine gray soil with a density of about 1.5 grams per centimeters cubed, but the regolith also includes breccia and rock fragments from the local bedrock. Glass can also be found within the regolith, created both from meteoric impacts and ancient volcanic activity. And due to the moon lacking an atmosphere, the regolith is constantly bombarded with micrometeorites and solar wind irradiation. These constant sources of impact break up the regolith particles and even melt portions of that lunar soil. And now I will hand it off to Julia, who will talk about revisiting some of the science for the moon.
Thanks, Ben. Now let's revisit the science. So what can we gain from all this information and from our mission with GLEE? We can gain a better understanding of lunar creation and morphology. It allows us to be more critical about mission landing locations, and for other missions too, beyond GLEE, an understanding of how the lunar surface affects our equipment. And if we know the composition and how it got there for the lunar surface and the moon, we could potentially apply this to other celestial bodies and move forward in the solar system. So how can we explore the moon specifically? Here, we can utilize our accelerometer on board our Lunasat and assess the gravity on the moon and how it changes by location. Our Lunasat can take small measurements of the surface gravity, which could aid other missions like GRAIL. With our thermopile, we can measure temperature. So we know we expect the lunar surface temperatures to change as we orbit the Earth. We can take measurements of this. We also know that the lunasats can be affected by the angle of how they landed and where. So taking measurements of this could even be your mission. Future application, as already discussed, can also help with potential landing sites, and it can give us a greater understanding of the lunar environment at a very small scale. So, why are we interested in lunar science? The GLE mission wants to make lunar science more easily accessible to everyone, as a new age of lunar exploration is on the horizon. In providing you and our teams with resources to begin your journey with the lunar science, we hope that you all will provide inspiration for those around you to help humanity achieve greater heights. So what's up next for you, and what's up next for GLE? To help teams visualize what they have been working towards, the communications and software subteams of GLE have been working collaboratively to bring you a new module that will help you put all of your knowledge to the test. Be prepared to work inside of Jupyter Notebook. We are excited to bring it all to you, so stay tuned.